Hi guys, I'm Connor Olhurst. I did your review for Chapter 13, Conjugated Systems and Diels alder, and I mentioned I wanted to make a review video for you guys about molecular orbital theory. I know you guys have heard about molecular orbital theory in class with the lectures and talking about HOMO and LUMOs interacting, but I think if you guys don't know how to draw each energy level, it won't really make sense to you. So what I wanted to do in this video was show you exactly how to draw each energy level for different molecules, and then show you how to solve some of the problems you might be asked on the exam. So to start out with, I'll draw the molecular orbital diagram for our simplest example, which is ethylene, or what our normal dienophile would look like. We have two sp2 hybridized carbons and two pi electrons. So we're going to draw two energy levels because we have two sp2 hybridized carbons. This scale is our energy axis. And we're going to draw this dashed line in the middle to represent a non-bonding level. For each carbon that's sp2 hybridized, we'll draw a dot on this line, which is where our orbitals will be. At the lowest energy level, we have all of our orbitals in phase, which represents bonding between them. So this represents the bonding, the pi bonding overlap in ethylene. Moving up one energy level, we get to the anti-bonding orbital, which has one node. Now a node is somewhere where electron density is not found, and across a node we switch the orientation of our orbitals. When we fill in each electron into this diagram, we start by pairing two electrons at the lowest level and then moving up a level. So this has two electrons, so we'll pair them here. This represents the HOMO, or highest occupied molecular orbital, of ethylene. Moving up one level is our LUMO. The lowest energy level is called pi 1, and any level above the non-bonding will give an anti-bonding orbital, and that's represented by the star. So pi 1 is our bonding orbital, and pi star 2 is our anti-bonding orbital for this molecule. Moving on, we can go to the next easiest example, which is an allylic cation. We can draw a resonance structure for this, showing that the positive charge is spread out between those two carbons. So we have three sp2 hybridized carbons and two electrons again. Since we have three sp2 hybridized carbons, we're going to draw three energy levels, and they're going to be spread out equally above and below the non-bonding level. So we have one below, one at the non-bonding, and one above. Since we have three sp2 carbons, we also draw three dots where our orbitals will lie. The lowest level, pi 1, has no nodes and has all the orbitals in phase. Moving up, we get one node, which we place equidistant in our energy level diagram, which would be in the center. And we draw on our nodes, flipping across each node. We draw on our p orbitals. Finally, at the top, we have two nodes drawn here, and we flip across each one. So this is pi 2, that's non-bonding. Pi star 3 is anti-bonding. Since we have two electrons, we'll fill them in down here. Now this structure doesn't look like either of our resonance structures, but if you remember, the best way to describe this molecule is to show the bonds spread across all three atoms, but with the cations, with partial positive charges on either end. And that's what this diagram represents. It shows the electron density spread between those three carbons. Moving along, we get to our diene, or just a structure with 4 conjugated sp2 carbons. So this has 4 sp2 hybridized carbons, and we have 4 electrons participating in the bond. So we'll draw 4 levels, 2 above, 2 below the non-bonding. This is pi 1, pi 2, pi star 3, and pi star 4. Since we have 4 sp2 hybridized carbons, I'll draw in 4 dots. Starting at the bottom, all these are in phase, no nodes. Moving up a level, we have 1 node, where we change the orientation of the orbitals across. Here we'll have 2 nodes. Up, down, down, up. And here we'll have 3 nodes, across which each change. Since we have 4 electrons, we'll fill in 2 here, move up a level, and fill in 2 here. Since this is our highest occupied molecular orbital, that's our HOMO, the next level up is our LUMO. I forgot to write that in here, but this would be our HOMO, and this is our LUMO. So again, this makes sense. If you look at the HOMO, we have bonding interaction here and here, which represents these 2 double bonds. We also have this structure, which represents electron density spread across all 4 carbons. And remember, the more you can spread out electron density, the more stable a molecule is going to be. This explains why this conjugated system is more stable than 2 double bonds in isolation would be. So if you had a molecule that looked like this, although that's pretty sloppy, if you didn't have a chain of sp2 hybridized carbons, you wouldn't have this added stability of the pi 1 orbital, or energy level. So the last example I'll do is for a pentadienyl cation. We have 5 sp2 hybridized and 4 electrons. So we're going to have 5 levels. Remember, this is non-bonding. Pi 1, pi 2, pi 3, pi star 4, and pi star 5. Each one will have 5 dots, since we have 5 sp2 carbons. Our lowest level, no nodes, all in phase. Next level, 1 node. Going up, we have 2 nodes. When we add 3 nodes, we have a node in the center, and spread between these ones. So this node in the middle cancels out the 3rd orbital. And finally we have 4 nodes, so in between each one. So, writing in our electrons, we have 4 pi electrons, so I'll draw 1, 2, 3, 4. Again, if you look at the structure, we have bonding interaction here, which is our pi bond. We have a node which shows there's no electron density in the pi orbitals, which is represented by the cation. And then we have this bonding interaction here. So these diagrams, if you work them out like this, they actually make sense. So this is our highest occupied molecular orbital, and the LUMO is the next one. So now that we know how to draw these, I'm going to look at 3 of the questions from the midterm I took last year. And there were 3 questions about molecular orbital theory, and they were really confusing to me at first. So I'll try to bring that up now. Yep, this is my test that I took February 19th, 2014. So questions 5, 6, and 7 have to do with molecular orbital theory. So they're just asking us to draw a HOMO and LUMO for number 5 and 6, which we just did. So this one should be pretty straightforward. We're looking to draw the molecular orbitals for this molecule, which should look pretty familiar. We have 5 sp2 hybridized carbons, 4 pi electrons. So we have 5 levels. I'm just going to draw in the ones we need. The p orbitals that we need. So the lowest has no nodes. And the next highest one has 1 node. This is pi 1, pi 2, pi 3 is in the non-bonding, pi antibonding 4, pi antibonding 5. So we have 4 pi electrons, so I'll put those in here. And then our highest occupied level is our HOMO. So once we draw this out, we see our HOMO has 1 node, and we just look for the one that has 1 node, and that looks like this one. So C is our answer for the HOMO. Now, this energy level doesn't necessarily look like what we're given. However, if you draw the resonance structure, just like this, it starts to make sense. We have bonding here, a node here, no electron density, and then bonding here. So that makes sense. That represents our HOMO. Next, they're just asking for the LUMO, so we draw the next level. The LUMO will have 2 nodes. So to place those equally, they would wind up on the 2nd and 4th dot that we would draw. So we'll draw 1 up, node, node, and then back up. That represents our LUMO. All we have to do is find the one that has 2 nodes with switching in between. And to me, that looks like choice E, which should be here. So we have 5 and 6 done. Now 7 is just a more complicated way of asking a molecular orbital question. The first thing you guys should know is that when a molecule absorbs ultraviolet light, electrons can get promoted like this. Don't be like that. To a higher energy level. Because the molecule's absorbing energy, that energy has to go somewhere. It goes to moving electrons up in an energy level. So we're looking for the result of the longest wavelength UV absorbance. So a long wavelength means low in energy. whereas a short wavelength would be high energy. So the first thing we should do is just draw out our energy levels for E135 hexatriene. We have 6 sp2 hybridized carbons and 6 pi electrons. 1, 2, 3, 4, 5, 6. So we're going to draw 6 levels. With our non-bonding in the middle. Pi 1, pi 2, pi 3, pi 4, pi 5, pi 6, with these all being antibonding. Our lowest level has no nodes, so they're all going to be in phase. Next we'll have one node, put that in the middle. Oops. Oh boy. So that's pi 2. Pi 3 will have 2 nodes. So filling in our electrons, we have 6 electrons. So I'm not going to bother drawing anything higher because we only have 6 electrons. I'll actually draw the next level in a second. So if we're absorbing UV light, we're going to be promoting electrons. We want the promotion that takes the least amount of energy because we have the longest wavelength. So since this scale is energy, the higher up we go, the more energy we'll need. So we could promote an electron from 1 to 6, but that would take the most amount of energy. 1 to 2 we can't do, so 1 to 4. But the smallest gap is between 3 and 4. And coincidentally, 3 is our HOMO and 4 is our LUMO. So we could move an electron up from 3 to 4 or to 5 or to 6, but the least amount of energy, since the scale is energy going up, we'll be moving one of these electrons up to pi star 4. I'll just draw this level in quickly for you guys. Let's see. Down, down, up, down. So we know going from 3 to 4 is the least amount of energy. So our choice is right there. If they ask about wavelength absorption, it's really just a way of asking about HOMO-LUMO interaction. Just a more complicated way of asking it. So I don't want you guys to get freaked out. The smallest energy jump, I doubt they'll ask you for the highest wavelength absorbance. Most likely it'll be the longest wavelength, if they even do ask that question. And it'll be the lowest energy, and the lowest energy is from your HOMO to your LUMO. Now, the last problem I wanted to go over was on a workshop that you guys missed. It was on what was supposed to be your workshop 2, but you guys had the snow day. However, this problem, although it's really tough, you really need a good understanding of molecular orbital theory to figure it out, which is why I want to go through it. So, it's talking about an analog to Diels alder, where seeing if this reaction going forward would make sense. Now, if you look at it, it could make sense because you just make these bonds move around and move the cation. But we want to see if we have a better reason to whether or not this would work. So, first I'll describe to you how Diels alder works, and then we can see if this works the same way. So in Diels Alder, in the lecture, he talked about HOMO-LUMO interactions. And that's actually the HOMO of your dienophile interacting with the LUMO of your diene. So our diene looks like this. That's the HOMO. This would be the LUMO, by the way. And our dienophile, our diene has these 4 energy levels. Why is this happening? So this is a HOMO, this is a LUMO. When we do our reaction, we're actually pushing electron density into the LUMO of the diene. So in order for that to work, let me draw out the HOMO of the dienophile and what the LUMO of the diene looks like. So this has up, down, down, up. If you think about this, going from the HOMO to the LUMO, so this is what our HOMO would look like, and we're going to something like this. So we have bonding interactions here, but not here, but not here. So, and that's what our ring ends up looking like. So we know that's the interaction is following these rules. So when we do a Diels-Alder reaction, the dienophile actually comes in either on top of or below our diene, which leads to our 2 enantiomers. So in order to draw that, I'll show, let me draw this out a little bit differently. I'm just drawing the opposite of what I drew before. So down, up, down, with this being our 2 nodes. So when our dienophile approaches, it's actually coming in from either the bottom or the top. So I'll draw what it would look like from the bottom. Just imagine this is below the other molecule. And as we move this up, we get interaction from this orbital and this orbital. Since they're both in phase, they can interact. Same thing here. Since they're in the same phase, they'll interact. Now the same thing will happen if we come from the top. So this was up. Let me draw it lower. Let's see. So as this molecule moves down, we'll see this interacts here, and this interacts here. So this overlap is what creates our new bonds, and it's what forces the HOMO to go to the LUMO, because you see it's forcing this one to switch up and then forcing these ones to switch down so that they overlap properly. So as the negative parts line up with the negative parts, or the empty and the empty, or going the other way, these line up. So in order for the Diels-Alder to work, we need to have the HOMO of the diene, the HOMO of the dienophile, and the LUMO of the diene matching up. So when we look at our analog, we have the same thing. Our dienophile is the same thing. That's what the HOMO looks like. But we have this allyl cation, just like before. That has 3 levels. And we only have 2 electrons in that, so this is our HOMO. The next level up is LUMO, with 1 node, so we switch electron density across. So let's see if they overlap properly. This is our dienophile, and this is what is acting as our diene. So we have something like this. Let me draw that a little better. With 1 node here, and we're crossing across the node. So as we try and line these things up, let me draw it a little clearer down here. Up, down, and then up, up. As we're bringing this molecule down, we get overlap here, so that's okay. This bond can be formed. But if you look at bringing this part of the molecule down onto this, we have phases, or we have different pi orbitals that are out of phase. So these cannot overlap. These will not create a bonding interaction. This one will. So in our problem, we can form this bond. That's okay. But if we try and do the other side, it won't form. Now when you just look at this problem by itself, you might think that reaction looks like it could happen. But in order to find out if it could really work, we have to look at the HOMO-LUMO interactions. And based on what we drew here, the HOMO and the LUMO don't line up. And because of that, this reaction won't work. So, molecular orbital theory is complicated, but it's a powerful tool for seeing how molecules will change when we're adding electron density to them, and whether things can work or if they can't work. I know this last problem is a little tricky. If you guys have any questions about that, or any questions about anything I went over, feel free to send me a message on Facebook. And I'll try and clear everything up for you before the exam. I hope this was a lot of help. Thanks. Good luck on your exam, guys.